All right. Good afternoon, everybody. Thank you so much for joining us on this beautiful Sunday. So today we've got something extra special for everybody. We have a very exciting lecture, but I do want to remind everybody of some of our Zoom tips and tricks before we begin. Before we get started, please make sure that you keep your videos off and your microphones muted. And this is so that all of the attention can be on our speaker today. And again, if you run into any issues, I know that there are lots of people here that come to quite a few of our lectures. So this sounds a little bit like I'm, repeating myself or deja vu, but if you do run into any technical questions or any technical issues, feel free to send me a message via the chat function. We will be taking questions from our speaker today. You can type those questions into the Q&A option that's on the bottom toolbar on your Zoom application. And again, he will be taking questions at the end of the lecture, but feel free to ask those questions or put those questions into the Q&A function at any point. Again, I know you guys that are here every week or every other week. This lecture is sponsored by the Mid-Cape Cultural Council as well as the Massachusetts Cultural Council, as well as our 2023 corporate sponsors. Those are Cape Air, Highline Cruises, and Avangrid. A big thank you to them for their generous support of our museum. And another little bit to note is that programs like this one today that everyone is watching helps come into fruition and is made possible by the support from folks like yourselves. I really urge you to consider donating or becoming a member today. Your support helps us host programs like this and many others that we host, so please consider donating today or becoming a member to help us keep our programs going. So today's lecture is presented by Captain Elliot Rappaport. He is an assistant professor of marine transportation at the Maine Maritime Academy. He's had a long career at sea that has been focused on the operation of sail training and oceanographic research vessels. He earned his BA from Oberlin College and an MST from the University of Maine and holds a 1,600-ton master's license. So, Captain Elliot, thank you so much for being here today, and I'll let you take it away.
All right, thanks so much. Let me share my screen, as we say in Zoom, right? Okay, well, first of all, thank you to everybody for coming. Thank you to Elizabeth and Abigail and the museum for hosting my talk. And welcome back if any of you you heard my talk earlier this year, or was it last year? Time sort of goes by. But in any case, the title of this talk is Reading the Glass. And that's actually the title of a book that I wrote recently about weather and ship operations and sort of life at sea in general. And hopefully you'll have a look if anything we talk about today is interesting to you. But primarily, actually, I don't, full disclosure here, I don't really think of myself as an author by trade or a meteorologist, honestly. But as Elizabeth was just saying in my introduction, I spent the bulk of my career at sea, about 3.5 decades as a captain of oceanographic research ships and sail training vessels, which are large sailing ships that are generally oriented towards the training of people in maritime careers. And that's been, bulk of my career has been at sea, although, as you just heard, a couple of years ago, I took a faculty position at Maine Maritime Academy, which is, like I say, is the other MMA. I know you have one up the road there in Buzzards Bay. But the maritime industry is a large one, and it spans a bunch of different branches. And like I said, I've been primarily involved in sailing ships and research ships, but that's only one corner of a very large industry. And I've got down in the corner of this slide, I've got this number, 11 billion tons. And that's a number I always like to throw into talks like this, just to kind of get the point across. What does that number stand for? Well, it actually stands for the amount of shipping that we can find at sea on an annual basis. There's 11 billion tons of shipping underway on the world's ocean each year. Another way of thinking about that is just about every object that's been made by human beings is going to spend at least some part of its life at sea on a ship, and sometimes multiple parts of its life. And this is a snapshot from a fascinating website. If you haven't been here already, called marinetraffic.com, and this is an aggregating site for the position data that's sent from most ships at sea at this point. In the satellite era of communications, transmit their operational data into a network that's then available to other vessels, and also just on the internet for tracking purposes. Is a device called AIS, or Automatic Information System. And if you're at sea, these data are tremendously useful for just tracking other ships, primarily for purposes of communication and collision avoidance. But when you're not, right, if you're a mariner on land, or if you're just interested in this sort of stuff, it's a very interesting place to go. Of course, here it doesn't look like there's any water left, that you could just about walk from one continent to the other on the ships. And it's actually not what it's like. Each of these is, looks like about the size of a jelly bean on the screen. And obviously there's more ocean in between. But a lot of ships out there. There's more ships at sea now than there ever have been historically. So we're, sort of at the zenith and still climbing in terms of the human age of marine navigation. What we're here to talk about today is a few things. As I was saying earlier, the book I've just written is primarily about weather and how it influences the world of shipping. So we'll be talking a little bit about weather, and I'll be starting with an introduction to some of the fundamentals, just to sort of establish a baseline, knowing that all of you are from different backgrounds. So this will be a review for some, and certainly not for others. And we'll start with just the most basic part of weather, which is where weather happens. Weather happens in the atmosphere, obviously, but it actually happens in a very, very small subpart of the atmosphere called the troposphere, which is about the lower 10 miles of the atmosphere. So if thinking about measuring the atmosphere in terms of height or thickness, the troposphere is just about 10%, or actually even less than 10% of the atmosphere's thickness. But because the atmosphere is made up of a series of different gases, and gases are compressible, the atmosphere is compressed by gravity, so that actually within these 10 miles of the surface, about 90% of the mass of the atmosphere, so we're talking about air, primarily nitrogen and oxygen, and water vapor, are all contained here. So this is where all the weather that we think of is going on. It's really just within this very, very thin layer. This picture is taken from space, obviously. And there's a famous quote about this phenomenon. An astronaut named Sally Ride, who went to space in the 80s, was just blown away by this phenomenon, just seeing how precious the atmosphere is, but also just how thin a layer it is. And she compared it to the fuzz on a tennis ball. That's just about right in terms of proportions. It's actually a little even thinner than that. It's about as thin as the skin on an onion, if you were to compare the troposphere, excuse me, to the overall diameter of the planet. Some other basics about weather. Weather is just driven by differences in density that occur in different parts of the atmosphere, primarily because of heating and cooling. We receive our heat from the sun. The sun actually heats the planet, and then the planet radiates heat back up into the atmosphere as infrared radiation. But at any rate, certainly we know intuitively, as residents of New England, that different parts of the planet, it's not fair, right? Different parts of the planet receive heat at different rates. So there are warm places and cold places. And as the planet warms and cools, the atmosphere warms and cools also. And here the physical properties of gas come into play. It turns out, when a gas is cooler, it occupies less space, it becomes more dense than the gas around it. And at the same time, if you have an area of atmosphere that is warmer, the gases there become less dense and more buoyant. So the warmer parts of the atmosphere, and this is a continuous process, and it's happening on multiple scales all at once, but sort of warmer areas of the atmosphere become less dense and more buoyant. The cooler parts of the atmosphere become colder, more dense, and they tend to sink. And in places where warm air is rising, this can be measured at the surface through the use of a barometer, something that measures atmospheric pressure. And areas where air at the surface is rising, pressure at the surface tends to decrease. And areas where cooler air is sinking, the pressure is increasing. So when meteorologists talk about things like high and low pressure, typically areas of low pressure is where warm air is being warmed, it's becoming less dense, and it's rising. And this is all ultimately being held in place by gravity in sort of an equilibrium. But the other thing that happens is air rises. It eventually will start to cool off, and it rises, it expands, it gradually cools off, and will cool off to some point. And eventually, another important component of the atmosphere starts to show itself, which is, as I said, the atmosphere is mostly made up of nitrogen and oxygen. But there's a significant amount of water there in the form of vapor. And when air starts to cool off, it will hold less water vapor. So we lift air up, we cool it off, and that triggers a process called condensation, which is just the conversion of water vapor into a liquid. So this water vapor is there nearly all the time. When we lift air up, we make it cold. A lot of that water vapor condenses to form clouds and maybe eventually rain or precipitation, right? If those clouds become concentrated enough, eventually the cloud droplets become large enough that they can survive the trip to the ground before they evaporate again. So that's weather, sort of in a nutshell. And you can expand or contract this diagram to sort of any scale that you choose, whether you're looking at global weather patterns or just sort of an afternoon rainstorm. Some more weather 101. When we think about weather in terms of zones of high and low pressure and start to think about weather systemically. And we have NOAA, the National Weather Service, to thank for this slide, but just basic introductory weather that you can find in any textbook. But we have areas where, as I was just saying, you have warm air that's rising. That tends to lead to areas of lower pressure at the surface. And we have cooler air that's sinking. That tends to lead to areas of higher pressure at the surface. And there's another element to this process, which is this thing called the Coriolis effect. The Coriolis effect is a rotational aspect that things in the atmosphere, that objects in the atmosphere get because the Earth is moving underneath them. So, we're observing the atmosphere from below. We're on a rotating sphere. And so things moving through the atmosphere, in this case, wind, tend to take on a curved path. Coriolis effect gets quite complicated if you actually try to do the math. But a simple way to look at it in terms of weather is that if you have a low pressure system, you have a place where air is rising, and as air moves in towards that area of low pressure at the surface, sort of air converges on the place where air is rising, and it tends to rotate in a counterclockwise direction, a counterclockwise or cyclonic direction. Now, if you have a high pressure system, exactly the opposite occurs. So if you have air that's sinking to the surface, it hits the surface and spreads out and is deflected by the Coriolis effect into a clockwise rotation. This is hemispheric, so this effect actually reverses in the southern hemisphere. If you go there, if you've been there, low pressure systems actually rotate clockwise in the southern hemisphere. But typically, we sort of ignore that in the explanation, just recognizing that it reverses. This said, this has nothing to do with what goes on in your sink, your toilet, or anything like that. I've been to New Zealand, and water in the sink does or doesn't swirl around in just exactly the same direction. But looking at larger systems, low pressure systems rotate counterclockwise, high pressure systems rotate clockwise. Some more weather basics, and again, just thanks to National Oceanic and Atmospheric Association. Weather is typically depicted when we look at maps. They show weather as areas of differing pressure, and what we call wind is actually created by air flowing from areas of higher pressure towards lower pressure. And this is expressed for mariners on something called a weather map using isobars. And isobars are just lines of equal atmospheric pressure. Very much like topographic lines. If you're looking at a topographic map, they use lines of equal elevation. And just exactly like a topographic map, the steeper the gradient, the steeper the change is, the steeper the slope is going to be. So, the more rapidly pressure is changing across the surface, the more wind you're going to get. And you can tell by looking at a weather map roughly by how quickly the pressure is changing, how rapidly the flow is going to be, or how rapid the flow is going to be between those two areas. So these lines, as I said, are called isobars, just lines of equal pressure. And mariners use all sorts of, mariners and other other people that are concerned about weather sort of on a day-to-day basis have all sorts of different graphical products that help them to identify these trends. We can look at weather globally, again, using the same principles of warming and cooling and differences in pressure. And if you heard my talk earlier, a year ago, we looked at some version of this illustration also, just to recognize that globally, weather is driven by the fact that the lower latitudes, the tropics, are a good bit warmer than the poles. And for that reason, the atmosphere in the tropics is continuously warmer, it's less dense. So air is more or less continuously rising up out of the tropics and being replaced from air from cooler latitudes from the north and the south. This horizontal flow across the surface of the Earth gives us a band of very nice steady winds in the tropics. They're deflected by the Coriolis effect so that we get this very nice steady band of winds in the tropics known as the trade winds, which are primarily easterly. And then we look at the air that's rising up out of the tropics and gradually making its way back towards the poles. The second sort of most identifiable wind feature that we can notice in a global sense, and that's much more relevant to those of us who are forced to live in New England, right? If you think about it, if you watch or listen to the weather over the course of a week or two, you'll realize that most of our wind, when we get it, comes from somewhere in the west. And that's because we live along a line of features that are sort of in this turbulent boundary between sort of warmer air from southern latitudes and cold air that's sinking in the poles. And that sort of boundary that we live along is actually something called the polar front. That's what makes most of our weather in the middle latitudes. So more to come on that. So if we flatten this out into a rectangular map of the world, what I'll call the sailor's ocean, we can think about global belts of wind. And as I've said, in the tropics are characterized by easterly trade winds, and the higher latitudes, sort of the middle latitudes. Again, here's the U.S. and New England. Most of our winds are in general from the west, and then finally, if you get into the very high latitudes, North Atlantic, the extreme South Pacific, there's another band of winds just kind of at the edge of the very cold polar air that is generally from the east. And again, sort of more to come on this momentarily. So these are winds at the surface. When we talk about weather, it's important to distinguish or at least recognize the fact that, most of us, we live down here on the surface and we're directly affected by winds at the surface, but weather is actually affected mostly by the channels of wind that are moving through the upper part of the atmosphere. And by the atmosphere, I'm talking about the troposphere. So the upper part of the troposphere, somewhere between 5 and 7 miles above the surface, is characterized by jet streams. Okay, and these are in general westerly winds that again sort of occur in the sort of main density boundaries between the warmer and cooler parts of the atmosphere. But because of the influence of the Coriolis effect, they generally blow from west to east. And these are fairly concentrated rivers of wind. And the one that actually has the most effect on our weather, again, sort of in the middle of the northern hemisphere, is the so-called polar jet stream. And that's the line kind of, or the channel between sort of warmer air in the middle latitudes and colder air sitting on top of the pole. But the jet streams work really in tandem with winds at the surface to provide what we think of as weather on a day-to-day basis. It's just another image of the jet stream. This is an animated, one of the many things, weather products that you can view online now. It's from a site called Null School. But this is an animated image of the jet stream, actually in real time, taken from weather models. And you can look at these and identify, this is actually the Western Pacific, but you can identify the jet stream as these channels of fairly rapid. This is wind is moving at about twice the speed of surface winds, and generally moving from west to east and splitting off into these fairly concentrated channels. Interestingly enough, we're not the only place that has jet streams. This is Jupiter, I think most of you recognize, and these incredibly very dramatic bands of color and sort of swirling patterns on Jupiter. We're looking at the upper part of Jupiter's troposphere effectively, and this very sort of west to east channelized effect, these that the colored bands on Jupiter take on are actually created by, it's exactly the same phenomenon. Of course, this is because it's Jupiter, everything is big. So, these are moving at, hundreds and hundreds of miles an hour. And, the planet is much larger and more massive than Earth. But in terms of physics, it's exactly the same phenomenon. So that was a 15-minute whirlwind tour of weather. If you want to come to Maine Maritime Academy, I teach a meteorology class that takes a semester, but as I've proven, it can be done in a whole lot less time than that. So let's take this to the actual practice of sailing. And this is actually a ship that I've been captain of a number of times, the Corwith Kramer. She's one of two ships that's operated by Sea Education Association right up the road in Woods Hole, Massachusetts. And so a picture of Kramer sailing along somewhere in the tropics, where the sailing is pretty good, right? The tropics are characterized, as we were saying, by strong and steady easterly trade winds. Okay, so very effective as long as you want to sail west, and pretty continuously warm and moist air. So there's a lot of what we call convection, which is this process of warm air being heated and becoming more buoyant and rising and creating these big puffy clouds, which we tend to connect with weather in the tropics. And most of the time, that's what you get. And then, of course, seasonally, this concentration of heat energy and moisture will produce tropical storms, which may eventually evolve into hurricanes. So that's the exciting weather that comes out of tropics. But those events are relatively rare when you think about conditions. All in all, for the most part, weather in the tropics is very consistent from one day to the next. Steady easterly winds and a lot of warm, moist air and cloud. On the other hand, if we go back to New England, this little star here on this slide is as close as I could get to Cape Cod. And we could see if, we were living in the middle latitudes or sailing in the middle latitudes, our weather is characterized by cyclones also. A cyclone is just a term that meteorologists use for a rotating low pressure system in the atmosphere. And our cyclones are created by the very pronounced density difference between, warmer air in the middle part of the Earth and colder air in the upper part of each hemisphere. And remember a few minutes ago, I was referring to this, and the boundary between these sort of semi-permanent air masses is what we call the polar front. And the low pressure systems, again, that kind of define our existence in New England, right? These are just sort of turbulent eddies that occur along the polar front and just involve the continuous mixing of cold and warm air. And if you look at the sort of standard, this is a satellite image, and I've drawn in the iconography that meteorologists use to identify the subparts of this system. But a low pressure system, an extratropical cyclone, just involves a swirling of warm and cold air, with a bunch of warm air being pulled up from the south, and then a bunch of colder air sort of filling in behind it, okay, to replace the warm air that's being pulled up from the surface to the south of the center of this system. And the circulation around the systems is a low pressure system, so we can recognize it as being counterclockwise. And we can also see that on the sort of the west side of the west and south side of the system, the wind is westerly, right? On the southern side of the system, it's westerly and warm, it's southwest. On the back side of the system, it's westerly and cold, it's northwest. And then above the system, it is easterly. So we can identify in this system, we can see parts of these global wind bands. We can have, westerly winds, okay, that are occurring on the sort of south side of these eddies, okay, and then we have colder polar easterly winds that are occurring on the polar side of these features. So each of these low pressure systems that we've been seeing a couple times a week all winter long, you can sort of think of each one of these as sort of a warm, cold, turbulent eddy that are happening along this continuous boundary, which is what we call the polar front. Okay, and if you look at this on a weather map, this is the stylized version of the same feature. So again, this is what it looks like in real life with the warm and cold fronts drawn in, and then this is what this feature actually looks like on a weather map, just sort of your textbook weather map. We have a center of low pressure. We have warm air that's being lifted off the surface. We have cold air that's filling in behind it, so colder, denser air. And then the boundaries in these systems are designed but defined by these features called fronts. And again, if you listen to the weather or you read weather forecasts, they're frequently talking about these fronts because the fronts are where the most pronounced changes in weather occur. And again, particularly, in this part of the world in wintertime, right, we get these very sharp temperature contrasts that occur when cold fronts pass. And the cold front is just the leading edge of this massive cold, dry air that's filling in behind the warm, moist, more buoyant air. And the cold front typically is where you get sort of the most turbulence, and also you get the most pronounced, the most active cloud features. The other things we can see drawn on this map, right? We talked about isobars, which are lines that define changing quantities of atmospheric pressure, and you could see near the center of a low pressure system, the isobars get closer together, indicating more wind, and then overall a counterclockwise or a cyclonic flow. So let's jump to sailing. Again, for those of you who heard my last talk, some of this will be familiar to you, but I like to look at, sailing's nothing new, right? Human populations have been making their way around the planet under sail for thousands of years. I always think as a sailor and as a mariner, and as somebody who's been predominantly a sailor, I kind of like to look back at older populations, just sort of think about, how all this worked for them. The answer is it worked pretty much the same way, right? If you look at as far as anybody can tell, the first Europeans to arrive in North America were the Norse navigators, the Vikings, if you will. It's confirmed that the only confirmed evidence of a settlement, a Norse settlement, is at a place called Lansom Meadows, up at the northern tip of the island of Newfoundland. They sailed here in open longboats, vessels that were fairly well suited to sailing downwind, and perhaps less so sailing back upwind. So if we sort of look at the prevailing wind patterns in the North Atlantic, we can see that almost certainly the Norse navigators took advantage of systems just like the one that we were looking at, right? They took advantage of the fact that sort of along the polar front on the north side of these low pressure systems, you could find easterly winds. And Newfoundland is a wonderful place, but I'm sure eventually they decided that they wanted to go home again. When the time came for that, they took advantage of the fact that on the southern side of these systems, you could find westerlies just as we saw. So they were able to sail, more or less downwind, sort of taking advantage of the fact that there are a few places to stop along the way, right? There are remaining Norse settlements in Iceland, and they had colonies in Greenland also. And then finally, they're farthest west in Newfoundland, and then sailing back to the east, taking advantage of the westerly winds on the south side of these systems. So I think I have a repeat of the slide that we were just looking at, right? And you can see how they were able to do this. So coming from the higher latitudes of Western Europe, what's now Norway, they were able to sail west on the north side of these cyclones where the winds were easterly, certainly quite cold and wet, but they were rugged. And then when the time came to come back, they could take advantage of the fact that on the south side of these systems, they were westerly. So, very direct and well-developed knowledge of meteorology, even though this was all 1,000 years ago. So about 500 years after the Norse navigators, right, the next Europeans to go to sea in a big way were, I'll call them the Iberians. They were, primarily Spanish and Portuguese. And, we know of Columbus and, his many successors. And, whether or not it was a good thing that they came to America, it was an impressive piece of navigation under sail. And it was accomplished in the same way, just through a gradually developed knowledge of the wind systems in the North Atlantic. This time they did it kind of in reverse, right? Columbus and his successors were able to get west based on an understanding that in the tropics you had an abundant supply of easterly winds from the trade winds. And then when the time came to come home, they were once again able to get back up into the westerlies. And this was all developed from this technique, this thing called the volta do mar, which is Portuguese for return to the sea. That was kind of the seminal discovery that actually really allowed the sort of second age of European world voyaging, if you will, to begin. Was this sort of revelation that you could, by sailing north again, you could jump wind bands. You could go from the easterly trade winds in the tropics, and you could get home again by jumping back to the north until you got yourself back into the westerlies and came home. And this was initially how the Azores were were discovered. There was no population there at all, as far as anybody knows, prior to the Western Europeans. But then they leveraged this technique to get to North America, and then ultimately, right, to sail globally. And what the successors of Columbus, or his contemporaries, really were able to take advantage of was this understanding, this gradually developed understanding that the system of easterly winds in the tropics and westerly winds in the higher latitudes was in fact global, right? And so that's what they did. They used this to sail and pretty much extend navigation on a worldwide basis. Okay, and so some of the names, right? There was Bartholomew Diaz, there was Vasco da Gama, who was the first European to get to India under sail, and then ultimately Magellan, who of course never came home again, but his fleet ultimately did, and Magellan's fleet was the first European fleet to undertake a complete circumnavigation. But they did, like I said, they did so by this understanding that whichever ocean basin you were in, there was a more or less repeatable pattern of easterly winds in the tropics and westerlies in the higher latitudes. So this was nothing new if you think about global populations. And what we see is if we look in the Pacific, there's an incredible collection of sailing cultures in the Pacific. The Polynesians are the best known, but by no means the only culture that populated the Pacific by sail. By the time the Europeans went to sea, most of the islands in the Pacific had been well settled, in some cases for thousands of years. This was all accomplished by open ocean navigation in open boats, what we would think of as sailing canoes, using some pretty spectacular methods of navigation. But we're looking mostly at this right now in terms of weather and what their sailing environment was actually like. And you can sort of see, just kind of skipping around the Pacific, it's generally agreed upon that the Polynesians and the other main navigating cultures of the Pacific sort of made their way out through the archipelago of Oceania, and then sort of gradually east and north across the Pacific, and kind of the last places to be settled by the Polynesians and actually humans in general. Hawaii at around 1200 AD, and New Zealand at around the same time, maybe later. But the central Pacific islands, Samoa and Tonga, were reached, in some cases close to 1,000 years BC. But the most interesting thing about what the Polynesians were able to do is that if you think about this is the tropics, and we're thinking, was already established, that the winds in general are easterly. They were in the trade wind belt, and yet they were able to sort of steadily make their way across the Pacific, and in generally upwind. That's fascinating for me to think about, because of what that really indicates is that they themselves had a fairly sophisticated grasp on some of the interannual weather patterns that provided some variability in the trade winds. And by that I'm talking about certainly the tropical cyclones, right, which occur periodically in the low latitudes, but also things like El Nino, right, which actually leads. We don't really have time to talk about that today at any great length. But El Nino is an interannual climate cycle that actually leads to some pretty direct and major interruptions in year-to-year wind patterns. And I think clearly they had some grasp of the signs of these events, so they could use them to make large passages sort of in between colonizations of the different land masses in the Pacific. So now in the here and now, right, people are still sailing around, mostly recreationally and for educational purposes, but you can see, nowadays relatively easy to track sailing vessels because everybody has equipment to broadcast their position. And we can see the routes are still, you can still trace the global wind patterns by the routes that modern sailors are taking. So we have, blue is west, right? So everybody who's going west is doing it in the tropics. And then everybody who's going east, for the most part, right, is doing it in the higher latitudes, somewhere in the like 35 to 45 degrees, a little higher, right? Everybody who wants to go, if you want to go from North America to Europe, you're much better off starting in New England than you are in Barbados. Okay, and that pretty much holds true worldwide. Sailing north and south is a little bit of an easier prospect, right? Because you can have the wind from one side of you or the other. So you can see that here is red, right? And the red is the north-south passages. And again, very easily identifiable here. Here's a trail, north-south red trail that goes directly through Bermuda, right? So a famous waypoint for sailing routes back and forth between New England and the Caribbean. Some of you may be familiar with. So question 3 is, since we've got 15, or what did I say, 11 billion tons of shipping a year, and most of these ships are, deep draft motorized cargo ships. And sort of the final question is, what do they care about weather, right? These ships, may have, 40 or 50,000 horsepower. The ships themselves are 1,000 feet long in some cases, and, upwards of 100,000 tons in displacement. And is weather still a concern for modern shipping? I guess what this picture should tell you is yes. Maybe some of you are commercial mariners, and most of the time, ships put to sea and on a day-to-day basis on a large, powerful merchant ship. Weather is not the same, not a factor to the point that it is on a smaller sailing vessel. But ships are still forced in a big way to be aware of what the weather is doing and what its impact on their operations can be. So there's still again, now more than ever, there's an incredibly well-developed network of knowledge and information sharing so that ships at sea can operate safely and in optimal conditions in terms of the weather information that's available to them. And like the slide says, right, this is the ONE APIS. And just about every year, there's some kind of a spectacular incident that involves the multiple loss of containers off of a ship. This is, they were on a regular route and got into conditions that, at least for part of their voyage, were beyond the means of their ship to hang on to its cargo. They lost about 2,000 containers in this event. So this is how information is available to mariners. Again, I expect many of you are, coastal sailors or have spent some time at sea. Weather is broadcast worldwide by different agencies. And broadcast by zone in great detail from, like I said, from a number of different national agencies in the U.S. It's the National Weather Service and the Ocean Prediction Center. So if you're operating coastally, you can get good, very detailed information hour by hour through a number of sources. Traditionally, it was just over the radio. Radio is still how signals get transmitted, but these days we rely more heavily on satellites rather than ship to ship or direct antenna to antenna transmissions, but it's the same information. It's transmitted either as recorded voice or as text information about what the weather is doing. There's also quite a bit that's transmitted in the form of maps, and this is a sample from a suite of maps that's issued 4 times a day every 6 hours by the National Weather Service Ocean Prediction Center. And this map is showing wave heights and directions with a satellite picture embedded. So it's one of 3 or 4 different products that ships will view, as I said, 3 or 4 times a day, and sort of planning their routes and adapting them to weather conditions. As is this, okay, and this is a wind and sea map of the Pacific, and actually at about the time of the ONE APIS, the container ship casualty that I showed you a few minutes ago. This is a gridded map showing wind and sea conditions. As I said, the wind is shown by these arrows, the arrows, these little feathered iconography here, and the arrows, 4 feathers is 40 knots of wind. This little green golf flag is 50 knots. So this is a Central Pacific winter storm from a couple of years ago, and so producing near hurricane strength winds and substantial seas. The units here are in meters, and so this is the significant wave height here. The highest third of the waves are 15 meters. So this ship was routinely encountering seas and 50 to 60 feet. Okay, so this is weather that ships in planning routes work pretty hard to avoid. Even full-size deep draft, fast commercial modern shipping spends a significant amount of time and energy working to avoid weather that will cost them time and fuel and ultimately do damage to their equipment. This is a sample of a product that's used of a commercial weather routing product, so sort of customized by ship most large commercial ships at sea use some version of this. It's a weather routing application that uses typically publicly sourced forecast information, sort of augmented with graphic enhancements and also input from private forecasters. Again, sort of designing routes that are hopefully customized to the capabilities of the ship that's subscribing to the service. So there's a large part of the support industry in the maritime field goes into weather routing and support. So I've got just a couple minutes, and I just wanted to talk sort of very briefly. We've got this incredible array of information about the atmosphere coming at us now, and where does it all come from? And it comes to us from weather models, from a very sophisticated network of, it's collecting information, processing it, and resupplying it as numerical as mathematical predictions of what the atmosphere is going to do. This data is collected in a variety of ways by, remote sensing, by sensors at the surface. It's collected by satellites and actually by ships, as we'll see. It's put into computer models that are sort of continuously generating gridded information about what's going on in the atmosphere. And it's very easy to say, but there's an incredible amount of data that's being handled just sort of almost invisibly to us, right? But in a moment by moment way, taking inputs of temperature, pressure, and humidity sort of everywhere, just about everywhere on the planet, and creating a three-dimensional grid that resolves how these differences are going to create flow, how they're going to create weather in the troposphere. This process is about 100 years old, although it's really only the last couple of decades that the computing power has grown to the point where models can process the atmosphere to the degree of resolution that's really useful. Like I said, the math has been around. The math was developed at the turn of the 20th century. So we've had the mathematical tools since then. The first time anybody actually did a mathematical forecast was in 1920, a British physicist named Lewis Fry Richardson. And it was a 6-hour forecast that the math took 6 weeks. Okay, so computing power has had to make its way to the point where we can actually create models soon enough to be useful to the people who are reading the weather forecasts. So this is what the math looks like. The equations, well, some people would look at this and say, well, these equations aren't really that complicated, but you need to realize the number of times that the number of times in the area over which they're being calculated is immense. And the computing power has gotten to the point where at this point, weather models can generate forecasts with a skill and accuracy up to about 5 or 6 days. With sort of overall ceiling, right, the mathematical limit of these processes is about 2 weeks. But effectively, the forecasts we're working from at this point are really accurate. The forecasters will tell you, about 4 or 5 or 6 days out to identify actual features and produce a reasonably accurate prediction of what's going to happen. Here's a picture of the one of the computers that this is done. There's a couple of different global weather models that do this. There's about half a dozen different modeling systems, but the ones you're most likely to hear about, and if you spend any time on the Weather Channel or something like that, they talk about there's an American model called GFS. There's a European model, the ECMWF, the European Community Medium Range Weather Forecast. And they're both run on supercomputers. The European model runs twice a day. The US model runs 4 times a day. But in any case, the American model takes 90 minutes to run on an 8.4 petaflop computer. Okay, and a petaflop has 15 zeros on it. Okay, a petaflop is 15 quadrillion operations per second. Again, so a lot. There's an unbelievable amount of data. And everything you hear about this process is unbelievably about the amount of electricity these machines use and the amount of data they can handle. But it's all in aid of producing the weather forecasts. And then finally, when you talk to the people that produce these forecasts, and they are desperate for data, right? Where does the information come from that goes into these models? And comes from satellites, right? It comes from aircraft. It comes from measurements taken on the surface. But the interesting thing about measurements taken on the surface, relatively easy to take measurements from land, right? We have, cell phone towers and airports and public buildings and things like that. But, what is most of the planetary surface covered with? Well, it turns out most of the planet is covered with water. And to take a measurement from the surface of the ocean, you need something that floats, okay? And that, for the most part means a ship at sea. So the National Weather Service and the weather services around the world have something called the Voluntary Observership Program, and they spend an incredible amount of time, working to encourage ships at sea to supply data, and this is done in a very methodical way. Ships at sea on ocean-going routes are supplied with the equipment and the organizational tools to transmit data back to the various weather services, and these data are used worldwide. But this is a statistic that they always present to you when they're reminding you if you're a mariner and you're, reminding you of how important it is to collect data at sea, which is that, for every 1,000 land operations, there's one marine operation. Okay, so that the global weather processing network is dealing on, say on a good day, right, 500 to 800 measurements on a single day that are taken at sea, versus 1,000 times that, right? So, 500,000, so close to 1,000,000, 500 to 800,000 terrestrial observations, and only 500 to 800 taken at sea, either from ships or weather buoys, which are incredibly valuable, but also fairly limited in the area that they're able to cover. And they always show you this graphic, right? Which is, there are huge parts of the ocean where there effectively aren't any measurements. And that really does an effective job to make you think about how challenging the job of forecasting really is. So what I think I'd like to do, I was hoping to spend a little bit of time talking to you about climate, but I see we're kind of running short on time. So what I would like to do is to wrap up there, and maybe if folks have questions about that or curious about that, maybe we can cover that in questions, but I don't want to run out of time to take questions from all of you. So I think I will wrap up there.
All right, wonderful. Thank you so much, Captain Elliot Rappaport. This has been incredibly informative. I have to say, when I was younger, I really wanted to be a meteorologist, and this is just the coolest stuff. So I wish I had a time machine and could go back. Although, such is life. So if anyone has any questions, please feel free to put them into the chat. You can also put them into the Q&A function. And while we wait for those questions to come in, would you be able to tell me a little bit about, your experience at sea and what really, how you got to become the sort of meteorology expert, and what got you interested in all this?
Well, I would hasten to add that I'm not a meteorology expert. I just, I think a lot of mariners get very interested in meteorology, I think because it's such an important thing to understand, and you want to be able to in a lot of ways communicate to yourself intelligently about what's going on, and also communicate with other people, whether it's on the ship or whether you're working with people ashore to discuss the weather. And I think there's just so many moving parts to it. If you have a short attention span, it's kind of endlessly fascinating because there's always another part of it to pick up and look at. But as far as a professional career as a mariner, the quick way to become a mariner is to go to a maritime academy, and I actually kind of came at it the long way. I grew up on Cape Cod and spent a lot of time around small boats, and just sort of gradually worked my way up into the industry. And that in part is part of why my career has been focused mostly around smaller vessels, sailing ships, and research vessels and things like that.
Fascinating. I mean, certainly the maritime academies that we have, especially in the Northeast, really, I'm glad to see that they focus a lot on navigation and how much weather has to do with navigating, and how much weather has to do with emergency management for vessels at sea. I was really fascinated in particular about how The weather is almost like a navigational hack, I guess you could say, although it's always there, to essentially get yourself across the ocean or across a body of water based on the weather patterns and the winds. I mean, I feel like I always knew that, but when you think about growing up in the 21st century, you think just like you said about the ONE. You think about you have these vessels when you're underpowered that are, so many thousands of horsepower. You don't really need to worry about the wind. You don't need to worry about the weather. You can just get there. You can just, drive yourself through it. But it really is so incredibly important, and understanding the weather patterns and the wind and how that's going to take you in different directions based on, where you are, literally from the difference between the Caribbean and Florida, and, you might hit that line around Maryland, completely
Right, yeah,
different
and
weather
the
patterns.
distances can be fairly small to make a big difference, and that's what, I'm teaching to cadets at the Maritime Academy, many of whom are headed for, careers on big ships, but to help them understand that, in some cases, it's not like being on a small sailboat, but at the same time, relatively small difference in route selection, could make the difference, even if it's not something as dire as losing 1,000 containers, it'd make a huge difference in fuel, just the efficiency of your operation.
Mhm.
I think sort of the more you can understand the patterns, and the more you can understand what there's incredible forecast products available, but the more you can understand about what they're telling you, um, ultimately it's still kind of up to you to look around and understand where exactly you are on the map,
Mhm.
because the grain size isn't always enough to tell you exactly where the wind is going to be doing what they think it is. And so that's, I feel like that's a skill that, wherever somebody's going in the industry, is still a really important part of the mariner's skill set.
It is very much a skill. So we've had a few comments. We've got a comment from Phil Wilson. He says, "Thank you, Captain R. Wonderful slides and your guidance through them." We've got a comment from Liz McCart from the Chatham Marconi Maritime Museum, CMMM. And she says, "Great talk. I heard you last year at CCMM and I read your book. It's fabulous. Always learning new things." So great kudos to you there for that. And Elliot, can you tell us a little bit about how to find your book? How do we buy your book? How do we get it? Can we buy it online?
Sure, yeah. Well, fortunately, it's been taken up by just a commercial publisher. So Penguins, Dutton is the publisher. They're part of Penguin Random House, and you can of course find it on Amazon. But I would encourage you to patronize your local independent bookseller, most of whom can get it to you just as easily as Amazon can. So,
Very
but
true.
thank you very
Very
much. Yeah,
true.
no.
We've got a question from Patrick. He says, "Which weather app do you enjoy?"
Oh boy, it kind of depends on what you're trying to do. If you're just interested in weather on your desktop, there's a great company called Predict Wind. It's actually a New Zealand company, and like so much else down there, they've really got it figured out, and they're very friendly. But it's there's a free version, and then for people who are actually going to sea, there's a very reasonable professional version. But that's a great one. There's a great website just called windy.com, which is it's a you know continuously operating kind of animated. It's all the weather model data that's being produced continuously. You can just log on, and it's completely, it's free, it's open source. You don't need to load anything, and get a continuous moving animation of anywhere in the atmosphere, and anywhere in terms of height. You can look at the jet stream, you can go down to the surface, and like that, plus the various public weather agencies that are putting out maps. That's an astonishing tool. The
Mhm.
challenge is it's tough to use at sea. A lot of ships really still don't have the bandwidth to access the internet in an active way. So it's more of a desktop tool, but that's another favorite.
Okay. I do have to say this isn't a weather app, but we do love at the museum. We love marine traffic. .net.com. I can't remember which
Oh,
one,
yeah,
but
it's
we do
addictive,
love.
isn't it?
It
Yeah.
is. It's so
Yeah.
much
Yeah.
fun. It's a great tool to have out there. We can, if we're ever, like what boat is that? We can just, look at our office window and we just look it up. Um, all right, so we've got another question from Falmouth's iPhone. I'm sure there's a person behind that, but Is it judgment or weather that causes disasters at sea?
Oh, I think somebody once told me that the answer to any question is it depends, and I think that's a place where that applies
Mhm.
also. And I always like to, well, like us wrong, but I think looking when things go wrong, you know, it's always almost possible to identify somebody who thought they were doing the right thing at the right time. So you've got to look at accidents pretty carefully, and it may be. Maybe a misjudgment of weather. It may be, uh, insufficient estimation of margins. Somebody who thought that they had more time or space to deal with than they ultimately did. And there's also, weather has a way of compounding other problems. If you have a mechanical problem or something like that. Um, so it's a big complicated. It's a complicated answer to a complicated question, I guess. Um,
Have you read a lot about, I'm sure because you work at Maine Maritime, the Portland Gale from
yes, yeah,
1888?
yeah.
So there's a lot of, I mean, of course, the captain went down with the ship, just like everybody else that was aboard on the steamship. And there was a lot of speculation that um, he was under pressure from the steamboat company to get ahead of the storm. And because
Mhm.
it was 1898 and they didn't have a lot of that, what we have with NOAA and, the windy.com and these great apps, they just kind of had to go. And there's a lot of sort of open source thought about, was he trying to make his bosses happy and just get out there and go and get ahead of the storm and get his passengers into Portland, Maine before the storm hit? Because maybe he had been a little hesitant before. And so, the owners of the line were kind of pressuring him to leave. Or did he just genuinely think that he could outrun it? And it's fascinating, the sort of conglomeration of those two weather systems that came up and made that sort of bomb cyclone, which most of us lived through in 2015, I believe it was 2014, in Massachusetts. And it's interesting to think that the weather reporting back then was still quite high tech. They would go into the office, the local weather bureau office, check what was going on, check the weather maps that had been sort of presented that day. Yet, they still had something like that happen. So it could be a little bit of both, or it could be, it depends. It's really you know,
Yeah, and in those sorts of cases, it's always a reminder that anybody who's operating in any kind of professional capacity, pretty much doing anything, is almost always under a lot of pressure from different directions, and some of it may have to do with your own feeling that you are able to get the job done, or perhaps a previous case where you feel like you've erred on the side of caution, and you feel like you
right,
still have to answer for that. Um,
right,
it's like so it's always very very difficult to look back and identify what was the crux thing that led a situation
right,
took a situation to such a terrible place. But it's complicated, right? And um, ships there are a lot of operational pressures affecting ships, and changing plans isn't is not always that easy. So it's often an element that you can find in these cases.
So we've got a comment from Ellen, New Hampshire, or Ellen NHUS. She says, "Thanks, Elliot. Very glad to catch this. Great slides and presentation from Ellen Connors from W79."
Yes, I know Ellen. Hello, Ellen.
And Phil asks, "Do you recommend house-based weather systems?"
By that, do we mean just like weather system for your front yard, that sort
Perhaps.
of thing? If that's the case, I
Yes. He
can't.
says
I can't
yes.
yet. That's something I keep promising myself I'm going to put in my front yard, and haven't gotten to yet. So call me in 6 months. I keep trying to do the research, and of course it keeps changing. I think that the best now, and it's getting easier and easier, if your system can be contributing real data, to the via the internet,
Mhm.
um, then that's probably to choose something that's the installation is high enough quality that's actually producing useful data for the overall information grid. I think that's the guidance I'm trying to follow, but I haven't gotten any further than that. Too much else going on. Yeah.
All right, so Phil, you got to check back in a couple months with Elliot. And we've got another comment from Liz McCart. She says, "What's the most harrowing weather event that you have sailed through?"
Uh, it's kind of hard to say. I guess it's a common question, but again, it sort of depends. I think, and I mentioned this a couple times in the book, that most of the time, like most weather at sea, it's more about endurance, and you spend a lot of time, sort of recognizing that you don't, your margins for things going wrong have gotten a lot smaller. But I've actually, I think that looking back, across a career of a bunch of years, I can still identify it was actually, a couple of things that have happened coastally. Sometimes the most frightening, like you know, one of the good things about being at sea in heavy weather is you have more room for things to happen. I still remember quite some time ago, it was midsummer. It was a beautiful summer day in Penobscot Bay. It was July or August, and cold front came through, and we had this very, very powerful, small, but very powerful. It was just a thunderstorm, a summer thunderstorm. But we had an incredible amount of wind and no visibility, and we didn't have anywhere to go. And it all worked out, but that was, like, still identify that, it's just a place we're having, if we were at sea, we could have just put the wind behind us and sailed away and let it go on its way. But there it was, dealing with. So I think probably looking at the most acutely scary situations involve dealing with, weather that by itself wouldn't have been intrinsically dangerous to the ship, but having to deal with it in close quarters.
Mm. So we've got another question from Hugh. He says, "What is your opinion of services such as Commander's Weather?"
I'm not familiar with Commanders specifically. I'm assuming that's one of the commercial weather routing systems. In fact, I think maybe I am. Maybe I do know about the company, but if it's one of a series of commercial weather routing services, I think most ships, most commercial ships at this point operate in some way with them, and I think they're it's certainly better than better than when they didn't exist. I think that the challenge is also making sure that the information is being processed on time, and that there's a good shared understanding of the information that's being sent to the ship. I think you can identify um, you can identify cases where people were looking at information that was provided to them, and weren't entirely clear on the latency of the material and things like that. So I see somebody else has chatted in who's got
Mhm.
experience with Commanders. I'm more familiar with a couple of other companies, but I see it's an awesome weather routing company, and I certainly wouldn't doubt that.
All right. So do we have any more questions for the Q&A or for the chat? Please feel free to sound off. And while we wait for that, can you tell me about one of your favorite experiences at sea?
It's another challenge. I think, I also, I think I make mention of this in the book. I think one of the things that I find most enjoyable about being at sea is, on long passages where sort of you're at sea for long enough that I feel like the beginning and the end of most trips are the most challenging parts for a number of reasons. And so where you're on a passage that's long enough that you feel like you can just sort of focus specifically on your time aboard ship. I've had a couple of long sailing passages across the Pacific that have allowed that sort of thing. But I've got, you get to go to a lot of places, and they're all interesting for different reasons.
Wonderful. So we've got a comment on windy.com. I can see the counterclockwise gyre in the Gulf of Maine, our area, he says, which I have heard about. It's pretty cool. And we've got a comment or a question from Phil. He says, "Any negative encounters with whales or subs?"
No, although it's interesting, I still remember, a long time ago when I took my first license exam, and there's a question in the navigation rules about, what symbol, what does a submarine show when it's motoring on the surface, and I, studied that, and I thought, well, I'm never going to see a submarine on the surface, and I think, the next trip after that I saw one, so they are there. Um, and no, all of my encounters with whales have so far been positive.
Mm.
They got
We
bad breath, yeah, but
Planktony, I bet. We had a visit from our former Sarah. We have a cat boat. Her name is Sarah, and our captain last summer is also a captain on a very, very large oil tanker or chemical tanker called American Endurance. And he visited the other day. He's on leave for a little while, and he was telling us about how they were off of Washington, and they were just cruising along right next to a pod of blue whales, and it was just incredible for them to see. Pretty much the entire crew came out to see it because it was just majestic. But yeah, they are out there, and especially on Cape, they've been some of the right whales have been swimming into the canal for fish, and then turning back around and leaving, which has
Okay.
stopped a bit of traffic through the canal, which I'm sure you can imagine is not great for shipping companies or any of the sort of ferries or Coast Guard vessels that need to get through. But they're out there. They're doing their things. All right. Well, without any other questions in the Q&A and in the chat, we will be signing off shortly. I do just want to remind everybody of some upcoming events we have. April 22nd, that's a Saturday, we have an ocean debris art workshop. We're going to be taking some trash and debris that we've collected from our local beaches and turning them into works of art. It is free with admission to the museum, and it will be going on all day. That's Saturday, April 22nd. We're open from 10 a.m. to 4 p.m. that day. We also have another class coming up on April 29th. This is an introduction to New England maritime wood carving. This is a very hands-on presentation, all about maritime wood carving in New England, name boards and all that fun stuff. That is a very intensive course that is from 9 a.m. to 4 p.m. It's a full day course, Saturday, April 29th. Our next lecture, just like this, is going to be Sunday, April 30th, and it's going to be about the exciting world of ice yachting. And this is going to be given by Deb Whitehorse, who grew up above her father's ice boat shop in Monona, Wisconsin. So they're going to be talking all about ice yachting. And please feel free to visit our website, tag us on social media, like us on social media, all that fun stuff. And don't forget to visit us. And I hope everybody has a wonderful rest of the weekend. And Captain Rappaport, thank you so much. Again, it's so great to see you, even though we are a couple states away. Feel free to come on down and say hi to us at the museum anytime.
Okay, fantastic. Thank you. And thank you to everybody for coming. Much
Bye,
appreciated.
everybody.